In the circuit shown, a 12-volt battery is connected to two resistors, one 1000 ohms and the other 500 ohms, and a capacitor of 30 times 10 to the negative 6 farads is connected in parallel with the 500 ohm resistor. The circuit's been connected for a long time, so all the currents have reached their steady states. In part A, calculate the current in the 500 ohm resistor. Since all the currents have reached their steady states and there's a capacitor in the circuit, a capacitor acts as a gap in the circuit, which means that you can treat the circuit as if this part over here where the capacitor is does not even exist. So we really just have to focus on what's going on in this part of the circuit, which is a single loop. So we can get the equivalent resistance. These two, if we just look at this as a single loop, these two resistors are now in series. So the equivalent resistance is just going to be 1000 plus 500, or 1500 ohms. So the total current will be equal to the total voltage divided by the resistance that we just calculated. So that will be 12 over 1500, which is 0.008 amps, or you could say 8 milliamps. For part B, draw an ammeter in the circuit in a location so that it can measure the current in the 500 ohm resistor. So we can put the ammeter, as long as it's somewhere in series with that resistor, it's fine. And truly, since the current flows all around this part of the circuit, you could actually put the ammeter anywhere in this part of the circuit as long as it's not over here where the capacitor is. So as long as you have the ammeter in series and in this part of the circuit, you're good. And draw a voltmeter in the circuit in such a location that it could measure the voltage across the 1000 ohm resistor. Well, voltmeters have to be in parallel, so you would have to draw a wire coming off this side of the resistor and put the voltmeter and then a wire connecting back to that other side. So for part C, calculate the charge stored on the capacitor. So since that capacitor is in parallel with the resistor, the voltage across this capacitor is going to be the same as the voltage across this resistor. So if we figure out the voltage across this resistor, we've got the voltage across that capacitor, and then we can just use the equation Q equals C times V. So the voltage across that resistor is V2. I'm calling this resistor R2, and the 1000 ohm resistor will be R1. So V2 is equal to I2 times R2. So the current through that resistor is the same as the current throughout the circuit, 0.008 amps, multiplied by 500, which gives you 4 volts. So that means the charge across the capacitor, C times V, is the capacitance, 30 times 10 to the negative 6, times the 4 volts, is equal to 120 times 10 to the negative 6 coulombs, or 120 microcoulombs. Or you could also put it in scientific notation and say 1.2 times 10 to the negative 4 coulombs. For part D, calculate the power dissipated in the 1000 ohm resistor. Well, there's 3 equations for power. It's I times V, or V squared over R, or I squared times R. And we could technically use any of these. We don't know the power, we don't know the voltage across R1, but we could figure it out really easily, because since we know the voltage across R2 is 4 volts, and the total voltage is 12 volts, and these are in series, that means there has to be 8 volts across R1. So since we know the voltage is 8 volts, we could use any of these equations, because we also know the current is 0.008, and the resistance is 1000. So I'm going to use this one. I'm going to assume we had not solved for the voltage yet, and just use I squared times R, which is 0.008 squared times 1,000, and that's equal to 0.064, and power is measured in watts. And for part E, let's say the capacitor is discharged and the 500 ohm resistor is removed and replaced by a resistor of greater resistance. So this R2 is just getting bigger. The reconnecting the circuit and then allowing the currents to come to their steady state values is the charge on the capacitor now going to be larger or smaller or the same. So we know the equation for the charge on the capacitor from earlier is Q is equal to C times V. The capacitance itself is not changing, so the only thing that could change is the voltage. So if the voltage across R2 gets bigger, that means the voltage across the capacitor gets bigger. If the voltage across R2 gets smaller, then that voltage gets smaller, and if it stays the same, then that voltage stays the same. So what happens to the voltage across R2? Since R2 is going up in value, R2 is increasing, that means that the overall current in the circuit will decrease, because the total resistance of the circuit is greater since they're just added together. That doesn't really matter in this case, though, because what matters is that the voltage across that resistor will increase. And the reason is because, through Ohm's law, V is equal to I times R. If you think about what would happen if, let's say for example, you put, in place of this 500 ohm resistor, you put a 1000 ohm resistor. Now this voltage and this voltage would have to be equal. Since they have equal resistances, they've got to have equal voltages. And since the total voltage still has to come to 12 volts, the only way that could work is if you have 6 volts and 6 volts. So by increasing this resistor, you're also increasing that voltage. So the V2 is going to go up, which means that the capacitor, since Q is equal to C times V, and since V2 is equal to the voltage on the capacitor, that means as the voltage on the capacitor is going up, so is the charge. So you can say that the charge on the stored on the capacitor is now larger.